Okay, so last week I did a session on Gaussian elimination showing the process if you are solving the equations themselves. So I thought that this week I would do the same thing, but I would do it by showing the process with matrices. Now I'm going to be doing all of these by hand, but I do have resources that I emailed out or that are in the announcements. I don't know if you have your announcements set or your Blackboard set that you get announcements emailed to you, then you would have gotten an email. If not, you would have to check the announcements in Blackboard in the classroom itself. But I think I have like 5 different links of places that you can use to do matrices for you, or at least to check your work. And I encourage you to use the technology because doing it by hand, it's fine for like if you have 2 equations. When you start getting bigger, it's really easy to make mistakes. So I encourage you, anything with 2 equations, to do by hand, but anything bigger, I would use the technology. It will just make your life easier. So this is essentially sort of, I talked some about last week about matrices, that it's just a way to write your equations without dealing with any of the variables itself. And it just kind of allows us to condense our work, save some space. When you do this, when you take your system and you just remove all the variables and put it into matrix form, that's called an augmented matrix. If you write just the coefficients in front of the x and the y and you ignore the constant that it's equal to, then you get what is called the coefficient matrix. So this is important, especially on the first assignment, because it tells you to write an augmented matrix. So that means you need to include even the right side of the equation. So knowing that vocabulary is important so that you know what it's asking you to do. So a matrix has like a spot for each number, and those numbers we call entries or elements. Usually I use the term element, but you can see entry just it's like a spreadsheet basically. Like each square on a spreadsheet, it's like an element or an entry. It's the same sort of thing. And we always refer to this as row and then column. So, and the row is always first. So if you are told element A23, that's row 2, column 3, because we always do row versus column. So if you're given the dimension of a matrix, which is basically the size, it's telling you the row first and then the column. So 3 by 1 means 3 rows, 1 column. So it's important to understand that knowledge or the vocabulary there, so you can make sure that you have the right size of a matrix, especially if you're using the online tools, because they will ask you how many rows, how many columns, or what's the dimension, so that you can create one of the same size. And if you're going into programming, this is really important because you can create arrays. You can even do an array inside of an array, which basically is a matrix. And you create those and you refer to them the same way, where it's always your row and then the column. So if the rows and the columns is the same, that's your dimensions are the same. It's literally a square. Otherwise, it's called a rectangular matrix. So the diagonal of a matrix is just that straight diagonal. If you're going from the top left to the bottom right, the diagonal is used the most when you have square matrices, because that's literally just, it goes from those corners. If it's a rectangular, it may not hit the bottom right corner, but the diagonal is always starting with the top left, and you're just going down down 1 row, over 1 column, and you just keep going down that way to get a diagonal. So if you're thinking of it in terms of like a line, it has a slope of -1, if you were to think about graphing it in a way. If this matrix has only 1 row, we call it a row matrix. If it has 1 column, we call it a column matrix. So last week we talked about row echelon form, and that your goal of Gaussian elimination is to get row echelon form, and that forms that sort of, it's an upside down stair step when you look at it in equation form. In matrix form, the goal is to have 1s in the diagonal. And since this is a rectangular matrix, not a square matrix, you can see that it doesn't hit that bottom right corner. You're going down 1 over 1 each time to get that diagonal. So you want to have those ones in the diagonal in order to get row echelon form. So I talked about in my last video the elementary, or I didn't call them elementary row operations. They were the allowed things you can do to a system. Once you call them matrices, they're called elementary row operations. It's the same thing, just different terminology. The steps are exactly the same. You can flip-flop to equations, but in this case, they're rows. And we actually have certain symbols that we use as shorthand to indicate this. So if you have like row 1 and row 2 and you're flipping them, then you basically do R with a subscript, and then you put an arrow between them to indicate that you're interchanging. You don't have to use capital R's. I usually do lowercase r's. You don't have to do A and B. You can do 1 and 2 or whatever, but that's just an example of what it could look like. We can still multiply, just like you multiply an equation by a constant, you can do the same thing to a row, because that's the same thing. It's just with that not written in equation form. And we indicate that by putting the constant in front of the row number. And then you can add a multiple of a row to another row, and then you replace one of those, this shouldn't say equation, this should say row, one of those rows with the result. So you indicate that by, okay, I multiplied this row by whatever constant C, I added it to row B, and now that result is going to be my new row A. So you kind of use that arrow to indicate what row it's being replaced in. So this is just some shorthand that you can use to show your work between each step to indicate what did I do from one step of the matrix to get to the other. So with matrices, we have what's called row echelon form, which if you have an online calculator is usually abbreviated REF, or reduced row echelon form, which is RREF. It's just literally an abbreviation. I have a graphing calculator T89, and these are the abbreviations that the TI-89 uses. I think the 84 does the same thing. So if you have a graphing calculator, you'd be looking for these things. Online websites that do this kind of thing will either use these abbreviations or they'll actually use the full name. But those are just the shortcuts if you're looking on a graphing calculator. And the difference between these two is that row echelon form has the one in the diagonal. Reduced row echelon form then goes further, so it does more steps to get ones above the diagonal. So it's row echelon form is you stop once you get to like the upper. If I kind of put a line here, you've got what's called a upper triangular matrix on the left, where you got the ones and then stuff above it. And then you could keep going for solving. We're solving for X, Y, and Z. And then that would give you reduced row echelon form. And reduced row echelon form basically gives you the final answer in the matrix. So you don't have to do any back substitution. So it's just a matter of when do you want to stop your solving for matrices. So the difference between these two is just literally the name of the process. So Gaussian elimination, which is what I'm going to do today, stops as soon as you have that one in the diagonal. If you go further and get zeros above each one, then you're doing Gauss-Jordan elimination. And so that is more steps to work through a matrix, and you don't do any back substitution because you can literally read your answers off the matrix. So if you're doing technology, I would say do Gauss-Jordan elimination and the reduced row echelon form because it gives you the final answer. But if you're doing it by hand, there's no reason. I mean, you can do either one. If you don't have to go all the way to Gauss-Jordan, you can stop at the Gaussian eliminations part and then use back substitution. So it's sort of up to you if you're doing it by hand, which method that you use. But there is a distinct difference. and that's in the names of the process. And the result looks differently. So it's important to know the difference so that you know what your final matrix is supposed to look like. So I'm going to be doing Gaussian elimination only for this session, because in my other video that I have on matrices, I do Gauss-Jordan elimination. So I thought, okay, I already have videos where I do Gauss-Jordan elimination, so let's do Gaussian elimination, and we'll do all those by hand. So I'm going to start with two equations, two variables. And so this is our system. We're going to solve this with Gaussian elimination. And so our goal is to get ones in the diagonal. So the first step is to write the system as its augmented matrix. So we want the augmented matrix. And matrices always have these brackets. So if you don't have the brackets, you're not actually writing a matrix. This is part of the notation. It has a bracket on each side. So I'm just taking the coefficients and the constants, just ignoring the variables, and then I've got 2 rows, 3 columns. So that's my augmented matrix. So our goal is the same process that I did last week, where the first thing you want to do is maybe try to get the 0 in the bottom left corner, because if you could try to do the first row, get that 1 first, but then you tend to end up with fractions. Like if I did that now, I would have all these fractions to work with. So I just saved that to the end. So I need to get a 0 in the bottom left corner. So that means I need to get rid of my -3 that's in the bottom left corner. So I can basically add these rows together. So it's like elimination. I've got a 5 and a -3, so I need to get those to be the same number, opposite signs. So I can multiply the first row by -3, or +3 actually, because I already have opposite signs. Second row by 5, and then add those together. So what we're going to do is 3 times row 1 plus 5 times row 2. So those will get the right numbers that will cancel out. And then that result is going to be basically stored in row 2. So I'm going to replace row 2 with whatever that result is. So that's my shorthand for what I'm doing. I will do my actual work sort of on the right, because I mean, you could just literally do this all in one step as long as you've got your calculator. 3 times 5 plus 5 times -3, and then replace that number. Or you can do it step by step and make sure you multiplied everything together. So if you were to do step by step and multiply, you would say, okay, first 3 times row 1, that would give me 15, 6, and 39. 5 times row 2 would be -15, 12, and -72. And then adding those together, 0, 18, 39 minus 72, that's -33. So you can show your shorthand like that if that kind of helps you keep track of what you're doing. And I do recommend doing that because it's so easy to make a mistake here. So after I've done that calculation, I'm going to rewrite my matrix. So my first row has not changed, but my second row is going to have 0, 18, and -33. So second step is, now I've got that 0 in the bottom left corner. I need that second entry in the second row to be 1. So I need to get that 18 to be 1. And we do that by dividing by 18. But we write this as multiplying by fraction. So it'd be 1 over 18 times row 2 is now getting stored in row 2. So that's going to replace row 2. That's something enough that I can do without any other calculations. My first row is untouched, 5, 2, 13, and then I get 0, 1, and then negative 33 over 18, which actually does reduce. I can divide those both by 3. It's negative 11 over 6. So now my second row is in the form that I want. And so now I need to get the first row, instead of a 5, I need that to be a 1. Now normally I work this vertically, but I'm sort of running out of room here. So I'm going to just go to the side here. And so to get rid of that 5, I basically need to multiply by 1/5. So we're going to do 1/5 times row 1, and that is going to be replaced, oops, and now put in row 1. So that's basically dividing everything by 5. So I'm going to get 1, 2/5, 13/5, then I have 0, 1, and 11 over 6. So now I'm in reduced echelon form because I have that 1 in the diagonal with the 0 underneath. And I have found out that y is negative 11 over 6. And now I need a back substitute to find x. So we're going to basically create these. Once you have it in this form, you go back to your equation form and you put it back into your system. So we have now the system, and the system needs to have that curly brace. So I have x plus 2/5 y equals 13 over 5, or 5. So plus 2/5 y equals 13 over 5. So that's what that first row of the matrix gave us. Second row tells us that y is equal to negative 11 over 6. So that's taking that matrix, putting it back into system form so we can do the back substitution. So I have y, so now I need to plug that in. So I have x plus 2/5 times 11 over 6 equals 13 over 5. So x plus, that will give me, let's see, I can reduce, divide those by 2. And so that would be negative 11 over 15 equals 13 over 15. Over 5. So if I need to get a common denominator, I need to multiply this one by 3, and then that would give me 39 over 15. So the right side is 39 over 15, so that is still equivalent. So I have x minus 15, I'm going to just rewrite this, minus 11 over 15 equals 39 over 15. So now I solve for x by adding 11 over 15 to both sides. So 39 plus 11 will give me 50 over 15, which then I can divide those both by 5, which gives me 10 over 3. And so now I have my final system. My x value is 10 over 3, and my y value is negative 11 over 6. And I'm going to write that as an ordered pair. So that's an example of the Gaussian elimination with a 2-equation, 2-variable system. The matrix part isn't too bad. You don't have to do a lot of calculations to do the Gaussian elimination. And then once you get to the point where it's in row echelon form, you put it back into equation form and then do your back substitution. So the difference between this and Gauss-Jordan elimination, which I demonstrated in my other matrix video, is that instead of doing this screen with all this algebra, you keep going with the matrices until you have the only numbers basically other than 0 and 1 are on the last column. And then you have your final answer. So the choice for you for doing this by hand is, do I want to do matrices the whole time, or do I want to stop at some point and then go back to algebra? So that's basically the difference between the two methods. Are there any questions so far? Okay. Timothy, you said your question is, so the initial step, is that the step for getting the augmented matrix that you have a question? Or is it the step after that? Okay, so I multiplied by 5 because, wait a minute, where did I multiply by 5? Apparently I can't multiply by 5 correctly. I'm looking at it now. Looks like I multiplied by 3 for 2 of those. Okay, so if you guys catch any math errors like that, you should catch it. Let me know immediately. Don't wait till the end, because now we need to redo everything because of those errors. So, and that's one of the reasons why I recommend you do technology here, because it's very easy to make these errors. So this is going to change a lot of things. And so now we need to basically redo the entire problem. So if you catch errors like this, let me know right away. Okay, so let's make sure that I'm actually doing that correctly. So 4 times 5, that should be 20, which will be 26. Negative 24 times 5, negative 120. 39 minus 120, that's going to be negative 81. So that's going to be 0, 26, negative 81. So instead of dividing both sides by 18, I'm dividing it by 26 for that last row. So that would be negative 81 over 26, which doesn't reduce. This is actually getting grosser numbers. Just double checking that is there any other math errors that you see so far before I go to the next slide and continue fixing this? Double checking myself. Okay, nobody's pointing out any other math errors. So we've got, this is negative 81 over 26. So then this needs to be fixed. That's going to be fixed. That changes. All of this changes. This is 81 over 26. Okay, so 2/5 times negative 81 over 26. I can still divide, it'd be 13 there. This will be minus 81 over 65. And so we still got our 13 over 5 over here, but we need to get that to have a denominator of 65. So I can multiply that by 13. So this is minus 81 over 65. That's going to be 169 over 65. 69 plus 81. We get 250 over 65. And then that reduces to 15 over 13. Or 50 over 13. Okay. So hopefully there aren't any more arithmetic errors there. But that would be the new correct answer. So I do recommend checking your work using technology so that you can catch if you make mistakes like this. I actually find it a lot easier to make mistakes with matrices than by doing it systems of equations because of the way that we write our steps. Because I didn't have the 5 written with a multiplication, it's really easy to just accidentally multiply by the wrong number, as you saw. So it is prone to error doing this by hand, which is why we encourage technology for this. Or any other questions or any other errors that you may see that I might have done in the arithmetic? Okay, so hopefully there's nothing else there. Okay, now I'm going to do a 3 equation, 3 variable system to show you doing Gaussian elimination by hand. So we need to get 1 to the diagonal here. First step is to get our augmented matrix. Oops. So my first row, I have 1, -1, 2, 2. Second row, we've got 4, -3, 1, -1. Now the third row, we don't have 3 variables, so you need to make sure you line it up correctly. So we have a 2 for the x, 1 for the y. We don't have a z, and then that's equal to 0. So this is what our augmented matrix looks like. You might want to double check, make sure there's no errors in signs, numbers, that sort of thing. So first row, we actually already have our 1 in the first place, so I would just leave that there. I wouldn't even try to change anything about that. I would just leave it there. Let's see, so looking at what we need to get zeros underneath that 1. So I'm actually going to do the bottom row first. So we need to make a 0 instead of the 2 on that bottom row for that first entry. So I can do that by multiplying the first row by -2, adding it to row 3, and then I can replace row 3 with that result. So maybe an alternate way to kind of show your work here is just to maybe write down and multiply by -2 here to help me not make that same mistake I did before. So -2 times row 1 would give me -2, 2, -2. Well, I still can't multiply apparently. -4, -4. And then we've got row 3, so that's 2, 1, 0, 0. I add those together at 0, 3, -4, -4. So Now my matrix, first row is unchanged. Second row is unchanged. Third row is now 0, 3, -4, -4. So we've got that 0. Now we need to get a 0 in our second row for that first entry. So in order to get rid of 4, I can multiply row 1 by -4 and then add those together. So I'm going to go to the next slide to indicate that. We're going to have a -4 times row 1 plus row 2, and then that result is going to be in row 2. So I'm going to just kind of do the math here again. So we want to do -4, so I'm going to just write that in. So hopefully I don't make any more mistakes. -4 times row 1. So we got -4, 4, -8, -8, and then row 2, 4, -3, 1, -1, 0, 1, -7, and -9. So that's going to be our new row 2. So I'm going to be doing a lot of flip-flopping here between slides. I've got a 1, -1, 2, 2, 0, 1, -7, -9, and then 0, 3, -4, -4. So we've got that first column now to be exactly what we wanted. So once you get that first column, then you move on to working with the second column. So the second column, we want to have a 1 in our second row. So we got that already, so that actually saves us some steps. We need to get a 0 underneath it. So I need to get rid of that 3 in the last row. And so I can do that by multiplying row 2 by -3, adding it to row 3. So we're going to do a -3 times row 2 plus row 3, and then I'm going to put that as the new row 3. So I'm multiplying this by -3. And you would be multiplying the 0 by -3 as well, but 0 times anything is still 0. So we're going to have 0, -3, +21, and a +27. Then we've got row 3, which is 0, 3, -4, and -4. And then we need to add those together. So I have 0, 0. 21 minus 4 is 17. 27 minus 4 is 23. So rewriting the matrix, you've got 1, -1, 2, 2, 0, 1, -7, -9, and then 0, 0, 17, 23. So now our second column is the way that we want it. Now to finish row echelon form, we need that 17 to become a 1. So we basically need to multiply the third row by 1 over 17. And then replace that third row with the results. And again, we're going to get some fractions here. So the first 2 rows are unchanged. Zero, 0, we get 1, and then we get 23 over 17. And now we're in row echelon form. But before I go on to my next slide, Are there any math errors that I did? I don't want to have a repeat of my last example. Is there anything that I multiplied or added incorrectly that you can see to double check just to make sure that my math is correct going forward? Okay, so I'm going to hope that that means that there isn't anything. So at this point, now we want to put it back into equation form because we're in row echelon form and we're doing Gaussian elimination. So we're going to put it back as an equation and then start doing back substitution. So I've got my curly brace and then I have x minus y plus 2z equals 2. So that's just putting those coefficients back in with the x and the y, the z. I have y minus 7z equals negative 9. And then I have z equals 23 over 17. So now we're going to back substitute. So I'm going to put z into my second equation so I can solve for y. So y minus 7 times 23 over 17 is negative 9. 23 times 7, so that's going to be minus 161 over 17 is negative 9 over 1. I have to get a common denominator, so I need to multiply that by 17. So we have y minus 161 over 17 equals negative 153 over 17. And then I'm going to add 161 over 17 to both sides. So that's minus 153 plus 161. This gives us 8 over 17. Now that I have y, I need to plug y and z back into our first equation so that way we can solve for x. So we've got x minus 8 over 17 plus 2 times 23 over 17 equals 2 over 1. And I know I'm going to have to get a denominator of 17 here, so I might as well do that now. So x minus 8 over 17 plus 46 over 17 equals 34 over 17. Simplify the left. Oops. That gives us minus 38 over 17 equals 34 over 17. And then 34 plus 38, we get 72 over 17. I don't believe reduces. So our answers are 72 over 17, 8 over 17, and 23 over 17. And I would not recommend trying to graph this or check by graphing because when you have 3 variable systems, the graph would have to be a 3D graph. So something like this, you would have to check some other method. Any questions? Do you see any possible math errors on here? Because again, it's really simple, really easy to make a error in your multiplication or your addition here. Okay. So I've got one more example, and this is a non-square system. I mean, it is rectangular, but I'm using the same terms that we did in the system of equations because we have 3 variables. We have an x, a y, a z, but only 2 equations. So this is going to have multiple solutions, and I'm going to show you how that looks when we solve using Gaussian elimination. So we start with our augmented matrix. So I have a 9, a 1, and -3, and a 21. Then a 0, a -15, 13, and a -8. So we still want to have that 1 in the diagonal and then a 0 underneath. And I'm going to work with that second row. I need to turn the -15 to a 1. And I will do that by basically multiplying that whole second row by 1 over -15. So I'm going to do multiply row 2, and then that's going to be the new row 2. We have 9, 1, -3, and 21 for the first row. Second row is now going to be 0, 1, -13 over 15, and then a +8 over 15. So I've got my bottom row set up the way that I want it. Now I need to have that top row, the first row, have 1 instead of 9 in that spot. So I need to multiply that by 1 over 9. So I'm actually just going to use the space that I have here. So I'm going to multiply row 1 by 1/9, and then I'm going to replace row 1 with that result. So we get a 1 over 9, -3 over 9, which reduces to -1/3, and then 21 over 9, divide that both by 3, 7/3. And then I have 0, 1, -13 over 15, and 8 over 15. So now we are in row echelon form. Now normally, I kind of prefer when I'm doing a system like this where I know there's going to be infinite solutions, I actually prefer doing reduced row echelon form, but it really doesn't matter. Now we're going to put this back into our system form. So I have an x plus 1/9 y minus 1/3 z equals 7/3. And then I have y minus 13 15z equals 8 over 15. Oops, system notation, so I need to have really braces. So what we need to do here is solve that second equation for y, and then plug it into the first equation and solve for x, so that way we have an expression of x in terms of z, which is going to be like our unknown. Our textbook will replace z with a, and we're basically just going to have everything in terms of a. When you do reduced row echelon form on something like this, that is already sort of done for you, which makes it really nice because then you don't have to do the back substitute. Like it just kind of takes care of it for you, and it doesn't get as messy. But then you do back substitution. So first, that equation with the y, I need to solve that for y, that second row, second equation. So that is going to be 8 over 15 plus 13 over 15z, or basically we let z equals a. So instead of z, it's going to be a, some unknown number. Now I need to replace y and z in my first equation. So I have x plus 1/9 y, and y is 8 over 15 plus 13 over 15a. Then I need to replace z with a, so that's going to be minus 1/3 a. And then that's equal to 7/3. And now I need to solve this for x. So this is going to get kind of gross with all the fractions. And I don't even see really anything that I can immediately reduce. 9 times 15, so that's be 135 plus 13 over 135a minus 1/3 a equals 7/3. So I'm going to have to get a common denominator here. So I'm going to have to multiply the ones with the denominator of 3 by 45 to get to 135. So x plus 8 over 135 plus 13 over 135a minus 45 over 135a equals 315 over 135. Okay, so on my left side, I'm going to combine my a terms. It gives me minus 32 over 135. And on the right, I'm going to take that 315 over 135 and subtract the 8. Give me 307 over 135. Oops, I missed my a. I don't think 32 over 135. No, that does not reduce. I don't think the 307 over 135 reduces. I am using the calculator button on my, or the fraction button on my calculator to help me there, because those are not ones that I can just immediately see and be like, oh yeah, that reduces. But doesn't look like it. So to solve for x, that's going to be x equals 307 over 135 plus 32 over 135a. So we put this in our final form with everything in terms of a to indicate that there are multiple answers. That was x. Y is 8 over 15 plus 13 over 15a, and then z is a. And so you've got this ordered pair. It looks gross because of all these fractions, but that's how this works when you have matrices. And so the steps are all the same. And if you're doing Gaussian elimination, once you get it back into the system form, it's the same steps that we did last week when we had systems of equations. So if you're a little unfamiliar with matrices and you feel comfortable with the systems, you could do Gaussian elimination and then you still have some system work. But I encourage you to use technology and do Gauss-Jordan elimination and do the whole thing in matrices, because then you don't have to do this back substitution and you're essentially just given your final answer to you in a way. How that would look here with a matrix is that basically, I'll do this in another color. So if you had done the row reduced echelon form and done Gauss-Jordan elimination, you would have ended up with a matrix that says 1, 0, 32 over 135 for the z. Actually, that would have been a negative. And then, oops, 307 over 135. Y would be 0, 1, negative 13 over 15. Oops. And that would have been 8 over 15. So I'm trying to like backwards. If we had gone further and done the row reduced echelon form, or then we would have an extra step. You'd have to get 0 above the 1. And this is what it would look like. And then you would still have to put these into equations and then essentially solve for the x and the y. Because it is non-square, it doesn't have enough information to give you a single solution. So just what that would be if this let me write this. This is reduced row echelon form. So if you tried to do that on a calculator, assuming that I made no math errors, you had a calculator that does reduced row echelon form, this system should end up with what I have in green. Are there any questions? Okay, so I'm bringing up the course right now because I just want to reiterate that I do have some resources for you with matrices. So this announcement right here, so there's several calculators that you can do to use for your matrices to make things easier. Double check yourself. I do encourage you to do that, but make sure you always write down the resulting matrix that it gives you. Don't just give me my x, y, and z. I want to see what the matrix looks like and what matrix you entered in. I do this video if you decide to type these things, but you are not required, and then some YouTube videos about them as well. So I recommend using these. I like this matrix.rashish.com. This is my personal favorite. It doesn't do the row echelon Gaussian elimination to get row echelon form. It only does Gauss-Jordan elimination. But you put in your dimensions. That's why I said it. You needed to know what your dimensions are. You enter in the numbers. You do have to be careful. I believe it doesn't allow decimals, so you have to do everything in fractions if you have any. But I like this calculator. I think it's really good. And actually, I'm going to enter in this system just to double check that we. So this is 2 rows and 4 columns. So that's, yeah. So you have to enter in if there was any decimals. So you actually, on this one, you get to choose. But the numbers are 9. 1, negative 3, 21, 0, negative 15, 13, negative 8. Then you hit solve. And so, yes, those are the same numbers. So it's indicating slightly different that x3 is as a free variable, or z. That's why we set it as a, and then you're getting the same thing. So this confirms the math that we did was correct, which is always important. So it got the same fractions. So I recommend doing this just to double check yourself. Anything that's with 3 variables, I would do using a calculator, and it does show you all of the steps. And you can see that it does it a little differently than I did it. It got a 1 up there first. It immediately did those fractions. I usually try to do those last whenever possible. And then it did get the 0 up there. But that's something that you can use to sort of check yourself as well. So hopefully this was helpful. I know matrices can be confusing at first, but if you're going into the computer science, where you might have to program some of these things in terms of arrays, or if you're going into the electrical engineering degrees that we have, you're definitely going to want to get familiar with matrices, and I would recommend any time that you solve a system of equations, you use matrices and technology, because it'll make your life faster, it'll be easier, eliminate errors, and then you can spend your time thinking about the actual electronics and then the engineering stuff. So any last minute questions or anything on that? Okay. Well, thank you guys for joining and for being flexible when I had to reschedule this, so I appreciate that. And hopefully I'll see you guys at my live for next week for week 4, where we'll be reaching the halfway point of the class. So guys, have a great Saturday, great Halloween, happy Halloween. Bye.